When you want to do experiments and want to learn something about one of the basic circuits, the so-called grounded emitter circuit, this is a good first setup test circuit that works very properly for all kinds of frequencies, both audio and high frequencies, even going up to say 600 kHz. This is the circuit how I made it in the past. I do nothing in my camera zoom, so anyway, two potentiometers here, and each potentiometer sets the amplification. This from the first transistor, this from the second transistor. Here are three transistors. The third transistor is set to a fixed amplification, 2 times approximately, and I want to demonstrate that. The amplification is set by the value from this resistor compared to that. Here it's 1000, here it's 2000, so this stage amplifies 2 times approximately. That's only theory, because in real it has a lot to do with the value of the capacitor that's on the emitter. So with 10 microfarad you will see a lot more amplification compared to 100 nanofarad. Furthermore, this is a completely classical circuit. Here you see the voltage dividers, 10K, 27K. Here also 10K, 27K, 10K, 27K, all the same. And you can see that you can vary the coupling capacitors. You can switch in 10 microfarad, also from stage 1 to stage 2, 10 microfarad, 10 microfarad to the third stage, and standard it is on 100 nanofarad. That has a lot to do with the frequency band where it works. 10 microfarad works good for audio, and 100 nanofarad works better for higher frequencies. And you can also switch that here. 100 nanofarad for higher frequencies, say 50 kilohertz up to 600 kilohertz, and the other for the lower frequencies. Decoupling unit, and it's very important to set the switches to the frequency band where you want to use the circuit. And you can also see here 3 switches, and with that switch you can switch in a 100 picofarad capacitor, and that will damp the frequency band where the transistor circuit works. But for higher frequencies, say you want to connect here a radio coil, you have to open these switches, because otherwise the transistor is much limited in amplifying the higher frequencies. As we know from the radio theory and the transistor technology, for a high frequency transistor the engineers do all that's possible to prevent internal capacitance. The internal capacitance in a high frequency transistor is extremely low, say 1 picofarad or 5 picofarad. And for the VHF transistors perhaps it's even smaller, 0.5 picofarad. I don't know that exactly, but you can study and find much more info, I'm sure, on the internet. So switching them on or off: on for audio circuits, open, switch these 100 picofarad capacitors off for the typical high frequencies, say 100 kilohertz up to 500 kilohertz, perhaps 1 megahertz. When you want to use this circuit higher than 500 kilohertz, the 100 nanofarad cap must be changed to, say, 404.7 nanofarad. And also here you can do experiments to go higher than 600 kilohertz. It's useful for audio 20 Hz up to 20 kHz. Switch these caps on. You can use this as an audio filter. That's also possible. In that case, connect your filter between the collector and the emitter, but use, of course, a coupling capacitor. Never connect the collector directly with a wire to the base here, because you have a shortcut, complete shortcut. And never do that here. Exactly the same. The circuit will not work. So when you want to use it as a filter, audio filter, take a coupling capacitor, mount your filter between the coupling capacitor and ground, take another coupling capacitor to the end of the filter and connect that to the base. Then it will surely work. For a first experiment as a filter, connect for instance here a 1 microfarad non-polar capacitor between the base and the ground, or do that here. You will surely hear that the sound gets very dull. Or for instance, take the coupling capacitor very small, say 4.7 nanofarad. Almost no low frequencies can pass through that capacitor. That's a very easy way to do experiments. The amplification from each transistor here can be set between the maximum that the transistor gives, that's approximately 300 here, and you can tune up the amplification by moving the wiper of the potentiometer more to the emitter. Of course, 300 multiplied by 300 multiplied by 3 or 5, that depends on this cap, or perhaps 10, is an enormous amplification, and you will surely see when you raise the amplification to the maximum that the circuit doesn't function properly any longer. That's absolutely sure. It starts to oscillate or whatever. I do nothing, by the way, and my camera zooms in and out. I can't help that, sorry. A very simple oscillator. Connect the capacitor here and connect the wire to the input. You will surely see that the circuit will start to oscillate. Or connect it here or here. Drive up the amplification. You will see the waveform change from, say, kind of whatever wave to a square wave. That's normal sine waves. When an amplifier amplifies too much, the sine wave will change into a square wave. The transistor is driven out to its maximum. Also interesting perhaps, you can make such a circuit frequency dependent by making a frequency dependent circuit normally consisting of a capacitor bridged with a resistor, and here a cap too, and here also a cap, and connected from the output here with a wire to the input. And you will see when the circuit doesn't start to oscillate, that depends on also on the frequency and on the phase, but try it. It's the best thing to do to learn something from it. You will see that the whole frequency, the amplifier gets a kind of bandwidth due to this part of the circuit. This is a frequency dependent unit. You can also omit the resistor or take a potentiometer here, then you can vary the bandwidth with the help of that potentiometer, or make another type of filter, connect it from the output to the input. Of course, never a wire directly from this location to here. It surely will not work. It's a shortcut. That are the important things from this circuit. I think it's a useful circuit. You can learn a lot from it, and when you meet kind of problems and you make later on another circuit or another small amplifier, then you can know how such an amplifier acts. Connect your scope, for instance, here. Send in a sine wave. Touch it with your finger. You can see the noise is very much amplified in this transistor amplifier. You can see how such an amplifier acts in a frequency dependent way, a kind of bandwidth, etc. A lot to do, a lot to work, and well, that was all. Wish you a happy new year.